Welcome to another video by Exact Engineering. The purpose of this video is to explain the use of complex numbers in solving engineering problems. What do we mean by a complex number? A complex number defines a quantity in size and angle, or size and phase shift. It is a multi-dimensional number. Can be in 2 dimensions, can be in 3 dimensions. It's not just size. We have a 2D complex number in Cartesian form, a plus bj. The a number is giving you the size of the direction in the horizontal. The b number is giving you the direction size in the vertical. A and b are both real numbers. The J operator, or as in some books, the I operator, if you're looking at a maths book, is an operator that defines a rotation of 90 degrees. Mathematically, it comes out to be the square root of -1, which will be explained later. What do we mean by real numbers? What we mean by real numbers is the natural numbers that we interact with in the real world. That includes things like your weight or mass, 75.3 kilos, the temperature outside, 20.3 Celsius, and so on. The J operator is imaginary because it's a square root of a negative number. Complex numbers are not complex, providing you understand the rules of algebra. Real numbers includes integers, whole numbers, fractions, and so on. Imaginary numbers are the square root of negative numbers. Why do we need 2D numbers? The reason we need them is some quantities need to be described with both size and direction or phase angle. So for example, in mechanics, forces can be at an angle, so they've not only got size, they've also got direction. So for example, the diagram here, if you stand on a floor in a building, the floor has to have a reaction that's equal and opposite to your weight. So the forces are equal, but they're going in opposite directions. So it's 2-dimensional quantity for force. Similarly, in the electrical world in AC signals, voltages and currents can be out of phase. Why would they be out of phase? They're out of phase, for example, in inductive circuits, in motor circuits, where the current tends to lag the voltage because we have magnetic field storage, and that skews the current to lag. So we need to define voltages and currents with both amplitude and phase shift. Other quantities like mass, time, energy, they have size only, so they're 1-dimensional quantities. In the electrical world, Ohm's law, Kirchhoff's law still applies, but when we are using those formulas, we have to use 2D numbers in AC circuits. We can have complex numbers in both Cartesian form, x and y coordinate pairs, or we can describe them in size and angle, which is polar form. As we said earlier, there's an example here, 7 minus 6j. The 7 is the horizontal dimension. The 6 is the vertical dimension. How do we know it's vertical? It's because it's got a j operator, which is explaining that there's a rotation of 90 degrees with respect to the horizontal. So the 6 is a real number, the 7 is a real number, that j is an imaginary number and represents a rotation of 90 degrees. Mathematically, j is a square root of -1. Why is that? If we look at a Cartesian form of a complex number, sheet of paper, 2-dimensional plane, for example, if we have a coordinate point on a map, point on a sheet of paper, it goes 5 horizontal, 4 vertical, we have an X and Y pair. We've got two perpendicular lines marking out 4 directions: positive vertical, negative vertical, positive horizontal, negative horizontal. So why is the J operator the square root of -1? So we will explain. If we have a dimension P, if we have a particular coordinate pair PQ, if we mark along P dimension in the horizontal, draw a line back to the origin, we have effectively a unit vector, which is length explains what its size is. And the angle with respect to a reference, which is normally the horizontal, gives its phase shift. If we rotate that vector into position Q, O to Q, what we have done is that vector is the same size as P. All we've done is rotate it 90 degrees. We use the J operator to indicate a rotation of 90 degrees. So O to Q is J O to P. It's a two-dimensional number here. The sizes are equal, and all we've done is rotated it 90 degrees as indicated by this J operator. If we then take that vector O to Q and rotate it another 90 degrees to get into position R, we've done two 90 degrees rotations. So we've got J times OP to get to position R. If we compare O to R with O to P, the size of the vector, the length is the same, but the direction is opposite. So the direction of O to R is negative O to P. That must mean by definition that J squared equals -1. J squared equals -1. J has to equal the square root of -1. It's an imaginary number. Represents a rotation of 90 degrees. And that's explaining, again, the J operator as to why it's a square root of 90 degrees. J represents a rotation of 90 degrees. If we rotate again round another 90-degree rotation from OR to point vertically down, we have then done 3 J's, 3 J rotations, J times J times J. J squared is -1, so that's a rotation 270 degrees of -J. If we rotate again to get back to where we started, there shouldn't be a J operator again because we're back to the horizontal reference. Just to double check, to verify that, we've gone to position Q, J, to position R, another J to 270 degrees, another J, back to where we started, another J, which is J squared times J squared. J squared is -1 times -1 again, gives you +1, which makes sense because you're back to where you started. One complete rotation of that vector from O to P, round, anti-clockwise, back to the start again. Anti-clockwise is a positive direction of rotation. If we have a position or a vector described in Cartesian form, for example, -3, 5, how do we get that into polar form, which is size and angle? So what we do is we use trigonometry to do that. So we have -3x plus 5y. We have a right angle triangle here formed by the vector from that point, Cartesian point there, back to the origin. We want to know the length of that vector, its size, and we want to know what angle it is with respect to the horizontal reference. Pythagoras, the sum of the squares of sides of a right angle triangle, 3 squared plus 5 squared gives us 34. We take the square root to get the longest side length, comes out to be 5.83 to 3 significant figures. To get the angle, we use the 3 here, the 5 vertical, we use inverse tan. This angle here comes out to be -59 degrees. We want this angle in here, So this angle in here is 180 degrees subtracted from that angle, which is 121 degrees from the horizontal axis. If we want to go from polar to Cartesian, how do we do that? Again, we're using trigonometry. If we've got a vector defined as length 7 and its angle is 310 degrees from the horizontal reference, we go round 90 to get to plus y, 180 to go round to that position, 270 to go round to here, 310, we're going round to this vector here and it's got length 7. How do we get that polar size and angle into Cartesian x and y coordinates? 7 times cosine of the angle gives us plus 4.5. Y coordinate, 7 times sine of the angle, gives us the y coordinate to 3 significant figures. So we go from the origin, we go plus 4.5, mark it off. We go vertical minus 5.3, we get an endpoint, we draw a line back to the origin. The length of that line is going to be 7. So that's going from Cartesian to polar. If we sum vectors, the easiest way to do that is in Cartesian form. So in Cartesian form, we've got the x and y components of each of those vectors, z1, z2. To get the sum vector, we're adding those vectors together, z1 plus z2, to get to this endpoint. Draw a line back to the origin. That dotted line, what is its length? All we need to do is to add the horizontal components together, 5 plus 2 to give us 7. We add the vertical components together, and the vertical is indicated by the J operator. 4 plus minus 1.5 gives us plus 2.5 J. That's the description of this vector in Cartesian form. If we want to multiply two vectors together, the easiest way to get the product of these two vectors is in polar form. If we've got size and angle, we've got two vectors multiplied together, z1, z2, fairly straightforward. We multiply the sizes to get 48, 6 times 8, and we add the angles. We sum the angles because we're multiplying to get angle plus 20, the product of two vectors. If we want to divide two vectors, the easiest way again to do that is to have the vectors in polar form. We divide the sizes and we subtract the angles. So we divide 6 divided by 8 gives us 0.75, so that's the size of the final vector. We subtract the angles, we got minus 30, minus 50, so we end up with an angle of minus 80 degrees for the final vector, z1 divided by z2. What if we have the vectors in Cartesian form? If we have the vectors in Cartesian form, the solution to the product of two vectors is a little bit more involved in terms of algebra. So if we describe them in Cartesian form, we have one vector 9 plus 4j, for example, the other vector 2 minus 8j. We need to multiply out these brackets here to have the result of 4 multiplications. The easiest way to do it is to take that number 9, multiply it by each of the elements in this second vector here. We add on the second element, the first vector, and multiply it by each of the elements in this second vector here. So we end up with 4 multiplications and we add them together. We're expanding the brackets. So we end up with 9 times 2. We end up with 9 times minus 8j. We end up with 4j times 2. We end up with 4j times minus 8j. And we add all these products together. So we end up 2 times 9 gives us 18. We've got 8j there, and we've got minus 72j there. If we add the j terms together, we can do that. However, What we need to watch out for at the end, where we've got 4j times minus 8j, we've got 4 times minus 8, which gives us minus 32. We've got j times j, right? J times j is j squared, but we know from previous work j squared is equal to minus 1. So instead of j times j, we can stick in minus 1. So we end up with 18 minus 72j plus 8j plus 32. We can add the horizontal dimensions together. 18 plus 32 gives us 50 in the horizontal. We can add the vertical dimensions together. Minus 72 plus 8 gives us minus 64. This is vertical, so it's got the j operator. And we end up with our final answer of 50 minus 64j. So the algebra takes a lot of focus. You need to get the plus and minuses correct. If you multiply a minus number times a plus number, the answer is minus, and vice versa. If you multiply two positive numbers together, you get a positive outcome. You multiply two negative numbers together, you get a positive outcome. So you need to follow the rules of algebra very carefully. If we want to divide two vectors in Cartesian form, it's a little more involved. We need to have our denominator as a real number so that we can solve it. We cannot solve it by dividing out two complex numbers. It's not solvable. So what we do is we use the trick of a complex conjugate to remove the j operator from the denominator. What do we mean by a complex conjugate? So for example, if you have a vector defined as 6 plus 4j, the complex conjugate is 6 minus. You just opposite the sign here. If it was 6 minus j4, the complex conjugate is 6 plus j4. You negate that operator there. Why do we need the complex conjugate? So we need the complex conjugate to solve it so that we get a whole number on the denominator. If you have a fraction, say it's 3 divided by 4, if you multiply both the top and the bottom by 2, you would get 6 over 8. 6 over 8 is still the same fraction as 3 divided by 4 if you divide it out. What we're doing here is we're multiplying the top, the numerator, the bottom, the denominator by the same number. So it does not change the ratio here. Why do we want to do that? We want to do that because we want a real number on the denominator so that we can solve it. So what we do in this example, 9 plus 4j numerator, 2 minus 8j is the denominator. We start off, we're dividing these vectors out. What we do is we divide both the top and the bottom by the same number so that the ratio is the same, but it has to be the complex conjugate of the denominator so that we get a real number on the denominator. So denominator is 2 minus 8j, so we're doing 2 plus 8j. So what we do is we expand these brackets out on the numerator, we expand the brackets out on the denominator. If you expand the brackets out on the numerator, we have 9 times 2, we have 9 times 8j, we have 4 times 2, we have 4j times 2, 4j times 8j. If you multiply the brackets out, we have 4 multiplications added together. We've got 18 plus 72j plus 8j plus 32j times j. 32 comes from 4 times 8, and the j times j, just leave that just now. We look at the denominator, do exactly the same process. 2 times 2 gives us 4, minus 8j, sorry, start again. 2 times 2 gives us 4, 2 times 8j gives us plus 16j, minus 8j times 2 gives us minus 16j, minus 8j times plus 8j, minus 8 times plus 8 gives us 64, but it's minus 64, and you've still got the j times j. Notice here, plus 16j minus 16j, if you add them together, they cancel out and you give you 0. Remember, j times j is j squared equals minus 1. So on the numerator, we add the horizontal terms together, 18. If j squared is minus 1, we've got minus 32 here. 18 minus 32 in the horizontal direction is minus 14. The vertical direction, we've got 72 plus 8j gives us 80j. On the denominator, plus 16j minus 16j cancel out to be 0. J squared is minus 1. We've got minus 64 times minus 64 times minus 1 gives us plus 64. We've got plus 64 added to 4 to give us 68 in terms of the x dimension. You'll notice here plus 16 minus 16 cancel out to be 0. You're left with a real number, which happens in this case to be a whole number, okay? So in the denominator, using the complex conjugate, we've got rid of the j operator from the denominator. What we can do now is take our numerator, which is still in 2D form. Minus 14 divided by 68 gives us minus 0.206. 80j divided by 68 gives us 1.18j. And that is the answer to the division of two vectors in Cartesian form. The algebra is quite complicated. You need to concentrate, you need to look at the signs, and you need to do it step by step. Get all the pieces of the jigsaw together. You're left with a real number, no j operator in the denominator. You can divide through and you can get the answer. Thank you for watching, and I hope that has been beneficial to the understanding of complex numbers.